Yes, hello. I'm Niels from Kiel University, and this is joint work with Nick Wu. So, as we have learned from the keynote, creating languages can be fun. And what do you do when you create a new language? Well, you have to define the semantics of that language somehow. And as we've done in the keynote, well, as we have tried, we've tried to write an interpreter. And those interpreters usually, if you try to just do it as an initial prototype, end up being a monolithic function. And what I mean by that is not necessarily that you write just one function without a local function, but that you define your function from your AST or whatever comes out of your parser, and it returns the result of the interpreter, basically. So what we usually don't have is modularity in the components of the AST. And I think that sort of contradicts the purpose of an interpreter, because when you write a new language, you might want to experiment a bit, or you want to add some features, you want to remove something. And when you have a monolithic interpretation function, that can be a bit difficult, because every small change might affect every part of that function. So you have to change lots of small parts. And I guess some of you have already experienced that. So when you think about what an interpreter does, it basically takes an AST, so a tree with different nodes, and it assigns semantics to that tree. And that's also something that effects and handlers do, because the effects represent a tree with nodes. Then the handlers are taking parts of that tree and assign semantics to that. So I thought, why shouldn't we use effects and handlers to implement interpreters? And if you have a look at the papers around algebraic effects, you see lots of different effects. So the basic ones are like non-determinism or state, and it gets more complicated with exceptions or parallel computations. But what usually is missing is the combination of those effects. So if you get lucky, you see the well-known combination of non-determinism and state, for example. So I think it's well known then that you can get a global state or a local state depending on how you run the order of handlers. But what happens when you try to interpret a whole programming language? Obviously, you're not going to end up with only 1 or 2 or 3 effects. It's going to be a lot more, like 10. And what I wanted to try is, can we actually write 10 effects that belong to the individual language features of a language, combine that all together into a large pipeline, and end up with something that is more modular and works at least as good as writing a monolithic interpreter. And for the language I choose to try this on, I decided for Curry on one hand, because at Kiel in the Imperial group, we developed the language Curry. You might have heard about it. It's a functional logic programming language, but also it has some pretty cool features, which I'm going to talk about in a minute. But for the beginning, I have sort of the result, a bit of a spoiler. This is just an overview of what I ended up with. So you don't need to have a look at the specifics, but I just want to show how this thing works. So what we have here is like this snake. That's the pipeline from, this is the input of the pipeline, and this is the result of the interpreter. What we have here is this proc type that enables us to express an AST, basically. We have this thing in the middle, which is the signature, so a list of effects that we have in the AST. And then we have A, or the last parameter here, which is the result type of this particular program. And as you can see, those boxes are connected by arrows which represent handlers. So each handler is going to remove one part of the signature. So the run partial handler is going to remove partial. And then we end up with a intermediate program basically that has one less effect in its signature, and we augment the result type in some way. As you can see, this is not necessarily always happening. For example, if we have a look here at the runReader function, handler, sorry, we see that this doesn't change the type of the results. But obviously it's going to change something, because if it weren't, then we wouldn't need this effect. So we can also have effects that change the result, but not necessarily the result type. And yeah, if we do this often enough, we end up with the result of the interpreter. And I'm going to get into a bit of more detail towards the end of the talk here. But I think for now, we should have a look at what Curry actually does. So Curry is basically an extension of Haskell. So we use syntax that we all know and love. So piano numbers, for example, would be defined like this, and then we can define addition on those piano numbers like we would do in Haskell. But what we can also do is that when we write a subtraction function, instead of writing another recursive function, we can reuse that add function by introducing a logic variable like from Prolog. So we if we have x and y as arguments, we can sort of write this equation that this introduced free variable z added to y should be x, and then this logic variable is also the result. So that's part of what Curry adds to the language. We also have a non-determinism, and I'm going to show that in a minute. But for now, what I want to focus on is that the fusion of a lazy language with non-determinism can lead to interesting results, because usually, aside from maybe some edge cases, you're not going to be observing the sharing in a language. But here, it definitely makes a difference in the values you get. For example, here you add two independent choices. So the question mark operator is the non-determinism operator. So it makes a difference whether you add two independent choices between 0 and 1. So then you get basically 0 plus 0, 0 plus 1, 1 plus 0, and 1 plus 1. Or when you share this choice, you only get two results. Because basically, this, as it's called call time choice, basically at the time of calling the plus function, you decide whether that non-deterministic choice is going to be the left branch or the right branch. And then whenever you have an occurrence of that variable, you're going to do what you decided at the time of calling the function. But obviously, because this is a lazy language, you're not actually deciding that. But it's, you're doing that just conceptually. Okay. What can we do with that? Well, we actually can desugar those logic variables into non-deterministic generator functions. So a generator function for nats would look like this, and it looks like a non-terminating function, and it actually is a non-terminating function. But what the laziness aspect of the language allows is that we can actually write basically the same as before. We just replace the free variable with this generator function. We can still use this function as before. So although we have this generator function that generates infinitely many values, the laziness will allow us to stop generating values as soon as it's obvious that this equation can't be true. Okay, so now we have the basics about Curry. How do we get to the interpreter? So in my case, I'm cheating a little bit, because as we saw in the keynote, writing the parser and that sort of stuff also takes time. we have the query front end, and the query front end takes query code and produces an intermediate representation called flat query. And that sort of removes all the more complicated syntax stuff. So we end up with a fairly small data type with, like, I think 8 constructors, which I then divided into semantically closed subsets. So all the language features that sort of belong together, I tried to put into a subset, and that are my effects. For each of those subsets, I then defined a handler, and then I combined all those handlers into a pipeline. And to sort of give you an overview of what effects I found in the language, I have brought you on the left side the overview of the effects, and on the right side a query program. And I'll show you which effects in the language I found, or I'll show you on the code where I found those effects. So if you are curious about what this program does, so this is the permutation sort algorithm. So the idea is when you want to sort a list, you just generate all permutations of the list non-deterministically, and then you just check all those permutations whether it's sorted. Because clearly, if you are going to generate all permutations, one of them has to be sorted, right? So aside from the performance aspect of this algorithm, it uses a lot of query's features. Namely, it uses non-determinism. So non-determinism clearly is one of those effects that you have probably heard of if you have done anything with algebraic effects. And we have that in the query language with the question mark operator, the choice operator, and we also have failed down here. By the way, if you're wondering why I wrote this lat here, I just had to add that because I want to reference a lat at some point, so it doesn't make sense here, but yeah. Okay, yeah, we have state. State is a very useful effect to have, as you would probably have guessed. When you're writing an interpretation function, you always have to keep track of something, mainly variables, also for renaming or for constraints. So state is an effect that I'm using often. I have the reader effect, which I'm using to insert the bodies of functions, because if you're calling a function, you have to get the body of that function from somewhere, and the reader effect takes in the program and then inserts the function bodies where it's needed. Yeah, I'm skipping the error effect because, I mean, yeah, I already put the let in here in a very, well, not required way, and I couldn't fit errors in here, so that's just for things like for the error function or undefined. I also have I/O, and that's basically for the I/O functions. And this sort of ends the category of algebraic effects. I'm going to talk about the different categories of effects in a minute, but for now, those effects which I've labeled here as algebraic are usually effects that you've already seen before, and those are effects that I've basically just reused in my interpreter. Those effects that are labeled scope, latent, and combined are things that I had to write specifically for query, although they could be reused for other languages, but I didn't find them anywhere else. So what else do we have? We have partial calls. So whenever we have higher order in the language, we're not calling a function whose name is known and that we can just look up in the program. It's going to be something that's specified by the calling function. So applying a function that is an argument to some other function, as well as supplying a function as an argument, is an effect in itself. And we also have the effect for constructing values. So we can construct literals and constructor-based values, but this also belongs into one effect with pattern matching. Because for pattern matching on a value, you need to know the head normal form of that value, so this sort of belongs together. And then we have memorization. So memorization in a lazy language like Curry or Haskell, for that matter, plays a big part, and almost every part of the language uses that to some extent. So whenever we introduce a variable, for example, in a function, in a pattern, or in a let, it's going to use memorization. And then I also have those combined effects. Combined effects aren't really a class by itself, but rather just the combination of other existing effects. And I think local bindings are used for variables. Renaming is also used for variables. And function calls is sort of a combination of all the other effects. So I didn't bother to add arrows to everything here, because in a functional language, obviously a function can do almost anything. So yeah, that's the overview. So I promised to sort of give a bit of explanation about this thing here, about these effect classes. And when we're talking about effects, often we're saying algebraic effects. And I mean, I think it's fine as a term, but it's not really true always, because not all effects are algebraic. So what algebraicity means in the context of effects is that all the nodes, or all the child nodes of a specific node, for example, the choice node here, should be treated equally when we transform the tree. And for non-determinism, this is fine, because we say we have two equal alternatives that can happen, and whatever happens, or whatever transformation we apply to this tree should happen to both parts of this node. But this is not always the case. I think the most prominent one where it isn't is the error handling effect, where you have this catch node, and we have this box here, which is supposed to be excluded from transformations done on the tree. And that's because this part, the box here, is going to flow into the tree through some handler later when the tree is handled. So we don't want to apply the transformation we're going to do twice to the continuation that we have down here. So scoped effects allow us to exclude some part from transformations to the tree, I guess. And then we have another very recent development, which are latent effects. And latent effects are basically the same thing as scoped effects, but they are a bit more flexible in the way where we can use those excluded parts of the tree. Because for scoped effects, we're always going to let this part flow back into the tree at the node, or the parent node, basically. Because as you can imagine, for error handling, the result of this part is always only going to go into this continuation, because it doesn't make any sense to move this part to any other catch, because it's specific to this one. But for latent effects, for example, for the memorization, it could be that the argument that we're memorizing here is only evaluated later, at some other point in the tree. Or it might be that it's not even evaluated at all. So latent effects allow us to delay this evaluation here indefinitely, and to do it at arbitrary points in the tree, basically. Okay, if this was a bit too abstract for you, I've also have an alternative explanation. So basically, the algebraic effects are the good old USB port. It has like full context, and yeah, it's very simple. Scoped effects sort of add a bit of capability to that, but it's sort of still the same, the same plug. And then we have latent effects with this sort of very strange connector here, and I'm not sure whether everyone in the room has seen it before. But we've seen that in the language here, we have all those aspects. And we sort of need to plug them into the same system. And how can we do that? Yeah, well, adapters is a great solution to that. There's this wonderful paper by Bunkenburg and Tom Schreiber's called A Framework for Higher Order Effects and Handlers that solves exactly this issue. So basically, we just pick one universal interface, and then we use adapters to plug all our effects into the system. And this allows us to have the simplicity, for example, of algebraic effects, where we can use it, but we also have the complexity of latent effects where we need it. And it also allows us to let the effects, well, we have to do some changes, but we can largely keep the effects as they are. All right, so I'm going to give a quick overview of how the handlers look in my pipeline, but I'm not going to show too much code. What we have here are the actual types in my program. So we already saw the proc before, and we also have seen this A here. But what's a bit different in reality is this part in the middle here. In the paper by Bunkenburg and Tom Schreiber's, they're using only a more general signature, but I found in order to have modular handlers in the sense that you can combine all kinds of handlers, so for algebraic, scoped, and latent effects, you need to sort of be a bit more concrete about your signature. So what I've done is I've split the signature into 3 different parts. So algebraic effects go into this signature, scoped effects and latent effects go into those 2. And then we also have this mysterious L parameter, which is due to the latent effects. And what a handler does in the situation is it takes a program where, for example, if you want to handle the non-determinism, it takes the non-determinism out of the algebraic effects signature. It adds some kind of semantic functor to the result. So we have the list functor here. And what it also does, due to the latent effects, we have to keep track of the semantics functor in this separate L argument here. And that's basically just the list transformer, I guess, but with the arguments flipped. So the L is not around the list, but inside. We can also do the same for scoped effects. So we can have one part algebraic and one part scoped, or we can do this for latent effects. So then we have something in the latent effects signature, and we're not necessarily adding modifying the result type as I said before. So with all those handlers, I'm also showing the handling pipeline in actual Haskell code. And what we can see here, we're taking a list of, well, programs in, and this proc is, the name expression would be more accurate, I think. But to handle that, we're running all those handlers in sequence, basically. Okay, so that's what I've done, and for the evaluation part of the talk. So what this approach gives me, obviously, is flexibility, because I have this pipeline, and I'm free to reorder all those handlers in an arbitrary way. And what this allows me is, for example, if I run lazy first and then run nd, I'm going to get the call time choice semantics I mentioned earlier. But if I just switch those 2 handlers around, I'm going to get a runtime choice. So something that would be probably a change that would need a significant amount of work in a monolithic interpreter is just switching 2 lines of code here. And I can also have 2 pipelines or more of them in parallel without duplicating code. What I can also do very simply is to extend the interpreter. So after analyzing the specification, I just have to add effects if necessary, write the smart constructors, and then adapt things in effects that are affected by the change. So here I did a small case study for adding logical unification, and it turned out I already had 3 effects that I needed for that. I needed to define one new effect for having a constraint store, but that's also just an instance of a state, so I had that as well. So realistically, I just had to define the smart constructors that implement the unification logic, and I had to adapt a bit of the pattern matching, because now I could also pattern match on 3 variables. So I had to just modify the parts that were interacting with this unification, but the rest could stay the same. And also I quickly had a look at the performance. As you can imagine, having multiple handlers run in a pipeline means that I'm traversing the tree multiple times. You can do something like Fusion for free to fuse that into a single pipeline, and this gives a considerable speed up, ranging from, I think, like 1.3 to 23 with an average of around 3. So that's not necessarily a problem. Right, to conclude, I found that effects and handlers provide modular semantics, which I found to improve the flexibility, the reusability, and the extensibility of my interpreter. I'm forced to make explicit design decisions, for example, the order of the handlers, which is also going to influence the result. And this even works for more complex combinations of effects. But what I've also learned from this whole process is that the accessibility of non-algebraic effects could be definitely improved, and also that the fragmentation of the different effect frameworks makes this whole process quite difficult. Okay, I've not really shown too much code in this presentation, but obviously that code exists. So if you want, have a look at the GitHub repository or the paper for explanations and for the full code. Thanks.
Do you mind going back to when you introduced the question mark operator? That's in the first, third part of your talk. So yes, this one here.
Yes.
So the let on the left is basically an effectful bind. In Haskell, we will express it using do notation. So do you have a universal bind in Curry? Where that let would basically give you the same value as the first line, the first expression.
Do you mean whether in Curry whether we have a let that gives the result of the first?
Yes, that's right.
Well, I guess it depends on the value you have here. If, for example, this was a closure, then you would get this result here. Or
I have to repeat myself. So basically, that let there, in Haskell,
yes,
right? That's an effectful bind, but which we use a left arrow. Now, as you know, in Haskell, there is this so-called universal bind, which we just use the let keyword for. So in Curry, do you have a universal let?
From your explanation, I don't think so, but I think we should talk about this later.
Hi.
Hi.
Casper Bak-Paulsen, TU Delft. Very cool work. I actually had 2 questions. First one is, you sort of touched upon the fact that when you permute the handlers, you get different interactions, right?
Yes.
Is that the only place where you get interaction? You mentioned that it was between lazy and, I think, non-determinism.
There are other places where things interact. For example, I think every handler that produces a semantics functor is going to interact with the other handlers. So this order of effect handlers here, I chose due to how I want the semantics to be. For example, I want either an arrow or a list of results, basically. You could also switch the order. Then you could have a list of errors, for example. So all of those things interact in some way. I think the handlers that produce some part of this result here are fairly fixed due to what you want in the result. But there are also handlers like the reader, for example, here, which you can, I think, arbitrarily position in your pipeline without really having too much of a difference.
Okay, thanks. Second short question. Have you thought about equations? That's one of the things that algebraic effects provide. Have you thought about it? Do you get an equational specification from this?
Equations?
Yes, equations for your effects.
Oh, so you mean specification?
Yeah.
Yeah, I've not really, well, those handlers don't really produce them, but I think it would be an interesting thing to have a look at for the interaction of those handlers, yes.
Hi, I'm Grant Van Domelen, Portland State University. I was wondering, you mentioned the accessibility and like the fragmentation of effect frameworks. What did you use when implementing this, and what like challenges did you find with them?
Yeah, I basically ran my own, which is sort of, it's not the best answer, but I think due to the relatively recent developments around latent effects, none of the existing frameworks explicitly promised that they are capable of doing that. And I found during the development, whenever you have some strange issues or a problem in general, it's always easier to have your own code base to have a look where things go wrong. But ideally, a good framework is going to solve many problems. So that's definitely something that's desirable.
Okay, thank you.